Okay, I know this is a long video, but this is going to be a really exciting one because today we're going to talk about combined loading. And everything we've talked about in this class so far has been leading up to this moment, right? We start the class, we talk about stress and strain, and then we start talking about all of the more specific types of stress and loadings, right? So we spend a lot of time talking about axial load, right? So that's when you have some member and you load it along its longitudinal axis. Often we label it with like a normal force. And you can have this in tension or you can have it in compression, right? And that's your axial load. So we spent a lot of time on this axial load. And then we talked about torsion, right? We spent some time on torsion. That's when we had these typically circular members that were being rotated, right? So they were being subjected to moments, and this was torsion. We talked about the stress related to that. And we've talked about the bending moment, right? The bending moment. So in a beam, pretend that beam is a little bit straighter. When you load up some beam and it starts to bend and deflect, we have some, I guess if I could maybe draw it like this, right? We have some beam that's undergoing bending. So this is our bending moment that we said caused a bending stress. And then also with beams, we had shear, right? So we had the beam essentially sliding against each other, right? In this transverse shear that we talked about. So shear, so we had that internal shear stress and a new shear equation. So all of these different things, all of these different types of loadings, and our pressure vessels. You can also have these pressure that can also cause stress. So all of these that we've talked about have been different forms of loading that you can put on some member that cause different stresses. So what we're going to do in combined loading is we're going to say, hey, in the real world, most of the time things are subjected to multiple stresses at once. They're subjected to multiple forces. Like, we're not looking at just axial load, just torsion, just bending moment. In a lot of cases, we're looking at multiple of these acting at once. You can think of something simple like a screw. For example, here's a wall. You put a screw into the wall, right? You screw it in with your screwdriver here, and you push that into the wall with the screwdriver. So not only is it being loaded with this axial load from you pushing down with your screwdriver, screwing that into the wall, but the screw is also experiencing that torsion, right? It's being screwed in, being turned into the wall. So a screw would see torsion and axial load at the same time. Or, another everyday example, you might see road signs, right? So when you're driving on the highway, and you go over go by one of those, exit now signs on the road, and it's being held up by these big gray, big metal posts. They say, Ashland Avenue, exit now, or whatever they say. They're being subjected to multiple forces as well. They can be subjected to the force of the wind blowing, right? So when the wind blows on this, it subjects this to a force, and it creates this twisting, right? This torsion about this point where it's fixed onto the ground. Or, say the weight of the sign itself. The weight of the sign itself can cause a bending moment, right? So there's a bending moment. There's axial load from the weight of the sign itself. A bird can come land on it, and increase our axial load, and our bending moment on our traffic signs, right? So there's often many, many things going on one particular member where we need to, account for all of these things. And luckily, we kind of already have learned a way of how to do this, right? The way we're going to combine all of these loadings for whatever scenario we're given is we're going to use our concept of superposition. Superposition, yay! Superposition is back! We learned about superposition a little bit way back in our axial loading video, where we said, all right, if I have one force that, brings this out this far, and then I have another force that brings the member out, it's acting maybe here on the member, pushing in, I can just add those two together, right? And so this one displaces this by this amount. This is the SparkNotes version. I talk about it better in the other video. But in the axial load video, we just said, hey, we can just add these together, right? We can add these displacements together. That's essentially the idea of superposition. I got two different things going on. To get the overall, I just add them together. And that's exactly what we're going to do with this combined loading. Right, so we had the some of those equations that we've seen before are all going to come back now. So when we had our axial loading, there we saw a normal stress. The normal axial stress we used was the normal force over the cross-sectional area. And for bending moment, that was another one that used normal stress. So the bending stress was moment times distance from the centroid over moment of inertia. And then all the other stresses we saw, other than, I guess there's pressure as well. Pressure was a normal stress. If you have a thin-walled pressure vessel, you could use PR over 2T or PR over T, depending on whether you're looking at the hoop stress or the longitudinal stress. And then we have, what else? In torsion, we talked about shear stress. Shear stress, that was torque times R, the radius, over the polar moment of inertia. We talked about shear stress in beams. Shear in beams, so that was our shear stress VQ over IT. And then this one, I think this is the shear equation that will come up most often. We did originally learn the average shear stress was V over A, but most of the time you'll be seeing this shear instead. The exact shear equation instead of the general shear equation. So all we need to do for any of these that we're given, we're just going to analyze which one of these are applied to our specific situation that we want to figure out. Because not everything will be applied at the same time. There may only be axial and torsion, like in our screw example. There may be more than that. So we only use the ones that are actually applied in our situation, find what we need, and we can add them together, right? So for our, let me make a little more room here. For our normal stresses, we're going to add all of our sigmas together. So all of our normal stresses, this in a different color. Normal stress is just going to be the sum of every one of these applied stresses that we have. The axial normal stress, the bending stress, any pressure stress that we might have. And same for our shear stress, right? Our shear stress being V over A if we have an average shear stress, VQ over IT, plus the torsion equation. Right, so it's just combining all of these together. Right, not too bad. The trickiest part is just finding all of the pieces that we need, making sure that we've captured all of the pieces that we need, and then adding them together as our very last step. let's kind of break down a basic step-by-step procedure on how you can go about these. So the first thing that we're going to want to do always, is we're going to want to section the member at the point of interest. First is section member at point of interest. So this is kind of a throwback to statics and internal forces, if we remember doing internal forces in 3D. Right? If I have some member that I'm sectioning, we're going to be working in 3D a little bit more in this combined loading. So I have I have some beam or rod or something, and I take a section through it. And so this is my cutaway. This is the cross-sectional area I can see when I cut through it. And then you can see the rest kind of going back towards the back there. So when I cut through that, remember I've got 6 different components here. We've got 3 forces and 3 moments. So a force in the Z direction, Y direction, X direction. I'm going to call this FZ, FY, FX, and this is labeled just kind of arbitrarily to kind of talk about it, where your shear forces that we would be seeing would be your Z and X here. So FX and FZ, those would be shear forces. And your Fy, the one in your longitudinal direction, is going to be your normal force, your normal axial force. Right, so your shear, that's where you're going to use your shear stress is VQ over IT. Your normal axial, that's where you're going to use normal force over area. So those are our 3 forces, and then you can also have moments. Right, so I'm going to draw each of these moments. Here's the moment about the z-axis, the moment about the y-axis, and a moment about the x-axis. So our moments about the x and the z-axis in this case, right, they're kind of in the same plane as the cross-section. The cross-sectional area is in this FZ plane. So they go around those. They are bending moments. These are the bending moments that use my over moment of inertia. And then our very last guy there, my, if we have an my, he is a torsion. And sometimes you will see this labeled as another arrow pointing out with like 2 arrowheads coming out of it. So sometimes you'll see it labeled looking a little bit something like this with a T. But this is the torsional moment. And that torsional moment, shear stress is torque times radius over polar moment of inertia. So you can see we can get pretty much everything that we need, all of those forces, when we cut through this cross-section and solve with statics. So that's going to be number 2 here, is once we make that cut through the cross-section, we can kind of see what forces we have going on. We want to find those forces, right? So use statics to determine the resultant normal, normal, not normal axial, shear, moment, bending moments, and torsion. So moments and torsion. A couple of things to keep in mind with this is that forces act through the centroid and moments act about the centroidal axis. Right, and the only reason I mention that is because sometimes your point of interest is not in the very center. It may not be on the centroid, it may not be on the centroidal axis of the cross section. It could be in another location. So just be aware that that is where the forces and moments act when we take them through this cross section cut. Because, you know, if we have, you know, a force maybe down here acting like this, and I want to take a moment, I need to be aware that this force is actually offset by some distance, by like the radius. So it's just good to be aware that all of these in our cut act through the centroid, act through the centroidal axis, and we need to pay attention to that when we're doing our statics to solve for all of these resultants that we need. So step three, once we have all of those forces, now we can see, okay, which properties of the geometry do I need? What cross-sectional properties do I need to go with some of these things? So if I have, for example, a torsion, right? So I have a moment in the y direction, as it is in this diagram, then I know I'm going to need to find the polar moment of inertia. But I may not need the regular moment of inertia. You know, I may not need Q. I may not need, you know, one of these other things. So find cross-sectional properties, I guess I'll call them. Find the cross-sectional properties that you need. So this could be area, this could be the centroid itself if you're given some kind of odd shape and you don't know where the centroid is, where the centroidal axis is. Maybe you need Q, which again, Q is y prime a prime, that cross-sectional area for this one. Area above the point of interest. Polar moment of inertia, regular moment of inertia, you know, any of these properties that you need to apply these different equations. And then your next step, once you have those, so we got all of our forces and moments, we got all of our cross-sectional properties, now it's just a matter of plugging them in. So for each one of these different stresses, we're going to go ahead and compute the stress. Compute the stress for each load component. Right, so we're going to go ahead and calculate all of these separately. And then at the very end, use superposition. Use superposition to calculate the stress. Or sometimes you'll see it calculate like the stress state. Calculate stress state of stress. Important thing to note is that we do always keep our normal stress and our shear stress as separate terms. These do not get added together. They do not get combined. If you're talking about the state of stress, you should have two separate answers, two separate stresses, normal stress and shear stress separate, right? Because our normal stress, if we draw like a little cube, they act in different spots, right? Our normal stress acts outwards, whereas the shear stress we see along the cube itself, right? So this would be the shear, and this would be normal, and this would be our shear. Again, they don't act in the same direction, so we would not combine them. Don't combine them, only add the ones that are alike. So your bending moment goes with your normal axial, and your shear goes with your torsion, so on and so forth. Let's go ahead and take a look at a couple of examples. In this example, we're looking at a little steel bracket here that's connecting two cables together. And it says if the allowable normal stress is 30 KSI, determine the largest force P that can be applied to these cables. So looking at this diagram here, it looks like we've got this little rod connecting them. It's 4 inches up off of the cables in the, I guess, Y direction here. And that the rod itself has a diameter of 1.5 inches. So if we go ahead and look at what we're given, right? We look at everything that we're given here. Our first step in solving these combined loading problems is going to be taking a section and finding those internal forces. So here, there's no specific location that they gave us that we're interested in finding the stress in. It just says the allowable normal stress is 30 KSI. But everywhere through here, our loading is going to be the same, right? We can take a section, really an arbitrary section anywhere through here, and we're going to get the same internal forces either way. So I'm just going to take, some arbitrary cut through the bracket here, and we're going to look at those internal forces that we have. All right, so if I take a cut through that bracket, draw it over here, kind of enhance, make it a little bit larger, cutting through the bracket there. We have the force P that's coming off of it that we want to find. And then there's our internal forces in here. So the internal forces in 2D are the shear, the normal force, and the moment. So we can apply our static equilibrium equations to solve for each of these. Right, so step 1 is we cut through the section. Step 2 is actually finding those forces. So we do our sum of x components equals 0, and we've got just 2 things in the x direction. N in the positive x direction minus p in the negative x direction. So, therefore, n equals p. That's pretty easy. Easy enough. N equals p. That's our first static equation. So we do have a normal force in there, right? So we know that we're going to be finding a normal stress. Let's look at our next one. Fy is 0, and the only thing in the y direction is the shear. So shear is 0, which means that there is not going to be any shear component, right? No shear stress component in this. Don't need to worry about that. And then our last one is the sum of the moments about this point. And that is going to be our moment that's about this point. And then our P force is also creating a moment, right? So the distance, this P force from where we're looking at here, cut through the middle. Well, let's just say it's in the very center of our rod here. It said that this distance was 4 inches, but if I'm looking at the very center of my rod here, I need to remember that this rod has a diameter of 1.5 inches. So if I cut right through the middle, because we know that's where the max stress occurs, I cut right through the middle, that's 0.75 inches, half of 1.5 inches. So it'll be the moment minus P times 4.75, right? That 4-inch distance plus, right, distance to the centroidal axis. Distance to the centroidal axis. So we have a bending moment of 4.75 P. 4.75 P. Again, we took it at the center there because we know that that's where the maximum occurs for our bending moment. All right, give myself a little bit more room here. And that's our first step. We found N, we found M, both in terms of P, right? Which was what we wanted because we want to determine the largest force P. So we've got the normal and the moment in terms of P. Now, the third step is to find any cross-sectional properties that are associated with them. So we said, all right, we have a normal force, so we have a normal stress, normal over area, and we said, all right, we found a moment. That means there's going to be a bending stress of my over I. So if we look at our cross-sectional area, cross-section of this rod, it has a radius of 0.75 inches, which we get because the diameter is 1.5, so half of that is 0.75. And we can calculate any of these attributes we need, right? So area is pi r squared. So that's pi times 0.75 squared. I get a cross-sectional area for that bracket. When I punch that into my calculator, 1.767 inches squared. Another property I need, moment of inertia. The moment of inertia for a circle is pi over 4 r to the fourth. So that's pi over 4 times 0.75 to the fourth. And I get a moment of inertia of 0.249 inches to the fourth. And then that y value distance from the centroidal axis to the edge, right? The furthest distance that can be is 0.75 inches. So in this case, we've got our y, and we've got all of our properties of geometry that we need to solve these two stresses. So we can go ahead and plug each of those in. That's going to be our second to last step here. Say, all right, I've got the normal force. The normal force was P. So this is P over the area we calculated, 1.767. That's our first equation. And then for the other stress we had a bending stress, and the moment was 4.75 P times y, 0.75, over the moment of inertia, 0.249. That's step 4. And the final step here is to use superposition to add all of these together. Okay, so all we do is to get our overall normal stress. That's going to be, I'm going to simplify this. So instead of 1 over 1.767, I'm going to make this 0.565. Same value, just written as a different coefficient. And then I'm going to go ahead and simplify this one as well. Plus, when I simplify this in my calculator, I get 14.33 P. So the stress is going to be 14.9 P. And now remember, we're looking for that P value. They gave us an allowable stress, and that is the allowable combined stress. That 30 KSI does not go in either one of these individually. It comes into this combined one. So I plug in 30 KSI here, divided by that 14.9 to get my P value. Gives me a P value of 2.01 kips. 2.01 kip. So that is the maximum amount that we can load onto the cables here so that the bracket does not exceed the allowable stress and break. Now we don't know necessarily which way it will break, whether it'll break from the axial load being too much and eventually like necking down and breaking that way, or if it will bend from the bending moment and fail that way. That we can't tell just from this calculation. But what we can say is we can say, hey, we can put a warning label if we're the manufacturer of these brackets and say, do not load more than 2 kips, right? that's our purpose here, is to essentially design so that we can keep everyone safe, right? Do not load more than 2.01 kips on this so that it does not fail. Let's take a look at another example. All right, let's take a look at a little bit more involved example. So in this one, we want to determine the state of stress at points C and D. So we're looking at two different points, C being on this very corner here, and D being on the centroidal axis of our cross-section. So here's our cross-section of our beam. It's a 50 by 250 millimeter cross-section. And then we're given this load diagram over on the left side. So as you can see, our point CD happens 1.5 meters from this pin over on the left, and then it goes through this angle. This angle is a 3-4-5 triangle. It's a 1.5, a 2, and then a 2.5. So this is just for handy reference, this is a 3-4-5 triangle on this angle. And we've got a distributed load on the slant and then a roller down here. Now for this one, your instinct may be, all right, our first thing is to say cut a section at the point of interest. So we would be cutting our section here at CD, and that would be correct, but we don't know our reactions, right? We've got this roller over here and this pin. We don't actually have the reactions there that we would need to solve for our internal forces at CD. So what we'll have to do first is solve for those internal reactions. And I'm going to encourage you to go ahead and pause the video here and see if you can work out those internal reactions yourself. It's a really good statics practice, a really good statics refresher for this. I'm going to skip that for now because I'm confident that you are pretty good at statics, right? You've made it this far. You've got a good idea of how the equilibrium equations work. You can figure out, what all of these reaction forces are. So my reaction over here is 97.6 kilonewtons. My reaction up at the pin is 21.93 kilonewtons. And my X reaction at that pin is 16.45 kilonewtons. So those are the reactions that you should get. Again, I would really encourage you to work them out for yourself using the 3 equilibrium equations for this beam set and finding those reactions. But these are our reactions. And now that we have those, we can go ahead and take our cut at our section CD. Let's take a cut and just see what kind of forces we're looking at here. What are the forces, the moments, so that we can know what kind of stresses are being applied that we need to add together. So if I take my cut here, it's pinned at that wall, so there's the reaction, here's the beam. Take my cut at CD, and I'm going to have the shear, a normal force, and a moment. And this distance here is 1.5 meters. Those two reactions again, 21.93 and 16.45. So now I get to go through the statics process again and solve for each of these. So I go through my statics process, or I say, okay, sum of X forces is 0. So my X forces here are 16.45 plus N. So that means that my N is actually in compression. My normal force is pointing inwards. 16.45 kilonewtons. I'm going to make a note. I'm just going to put a C next to it to note that it's in compression. It's not actually in tension as I'm showing it here. And some of my Y forces, I've got 21.93 minus the shear. Oh, well, that one's even easier. 21.93 kilonewtons. And then I take a moment about that cut. And I've got the moment value and then times, or sorry, minus 21.93 times the distance away is 1.5. I punch that in the calculator to get my moment value of 32.89 kilonewtons. Right, so I have all three of these components working on this beam. So I've got the normal stress, which is the normal force over area. I've got the shear. Shear stress is VQ over IT. And I've got the bending moment, MY over I. Right, no torsion here. Just my other three common stress equations that we see. So as I'm looking at this, we're looking at these two different points, right? So let's kind of look at what's going on at each of those points. If I look at my normal stress, I'm going to kind of draw, here's the cross section of my beam here. Right, my normal stress is going to be the same, it's in compression. It has the same value no matter where I'm looking. So it doesn't matter if I'm looking at point C or at point D, they're going to have the same normal stress value. So I can go ahead and compute that. Right, it's just the normal stress over the area, so normal stress in either case for C or D, since it is constant, right? It's just a constant all the way across here. Is going to be the normal force, 16.45 over the area. Area is 0.05 times 0.25. And that comes from this cross-sectional area, the 50 millimeters by 250 millimeters. I just went ahead and converted them into regular meters. And if I go ahead and punch that in, then I get the normal stress is 1.32 megapascals. 1.32 megapascals for this normal stress. But we'll notice if we take a look at our shear stress, right? So again, I have my beam cross-section that I'm looking at. Shear stress, we know, has no value on the outer edges. And then as you go towards the center, that's where shear is a maximum. Right, so there's like there's little shear, and there's more shear, and there's a lot of shear in the middle, and then it goes down again to nothing at the edges. So it looks something more like a parabola, a parabola of stress. A parabola of stress in that cross section. So if I'm looking at point C, right, there's actually no shear stress there. There's no shear stress at point C, which makes sense because there's no value for Q at point C. Remember, Q is that area times the centroid, but there's no area above point C. It's on the very edge, so it has to be 0. So our shear stress at C is going to be 0. But our shear stress at D will have a value. So it will be that VQ over moment of inertia times T. And we need to find a few more things before we can actually solve this one. So I'll come over here and we'll do those few more things in a second. But before we do that, let's go ahead and look at the bending stress. The bending stress, when I look at the cross section, right, we know that at the neutral axis, here's our neutral axis, our bending stress is 0. It goes down to 0. And that's because in our bending stress, what happens is we have one side that goes into tension and one side that goes into compression, right? When you imagine taking your, taking a stick or something. Here, I take this book and I bend it, right? So the top would be in tension and the bottom is in compression. So what that looks like is that our highest amount of stress is happening at the ends, right? So it's going into it. There's high amount of stress, and then it's smaller and smaller until we hit the neutral axis, and then it comes back out, right? So it's going in, here is being compressed, and then all of a sudden it switches at the neutral axis and comes back out. Gets bigger and bigger until we hit those edges again. So there's C, and D is on the neutral axis there. So for this guy, our bending stress at C is going to be at a maximum, right? It's all the way out on the outer edge. Our bending stress, my over moment of inertia. But at D, there is no bending stress. It's 0. Which again makes sense because the distance y between the centroidal axis and our point of interest is 0. They're the same. So since that y is 0, that means that our overall stress at D is 0. Oh, why does that look so terrible? Let's write that better. All right, this is D. There we go. So now we know what we need to find. Right, we need to find moment of inertia, I, and we need to find Q. So let's go ahead and look at our cross-section again. So we need our moment of inertia. That is the same in any case, right? It's a property of that overall geometry. I draw this guy again. He is 50 by 250 millimeters. So the moment of inertia for a rectangle, since he's just a basic rectangle, nothing composite, nothing weird about him, 1/12 base height cubed. Right, just use the basic rectangle moment of inertia since the cross-section is just a rectangle. So 1/12, 0.05, that's just converting into meters, and then convert the 250 over 0.25 meters cubed. So I get the moment of inertia for this guy is 6.51 times 10 to the negative 5th meters to the 4th. Right, so that takes care of I for both cases. Our y for our C case, y is just going to be the distance from the neutral axis to the outer edge. So in this case, y is going to be 0.125. Right, that's half of 250. And then let's take a look at our D condition for the shear stress. We have everything now that we can solve for this. Actually, let's go ahead and do that. Let's just go ahead and solve for the bending stress. So this is the moment, what did we say that was? 32.89 kilonewtons times 0.125 meters over the moment of inertia we just found. 6.51 times 10 to the negative 5th. So I just punched that into my calculator to get 63.2. Right about 63.2 megapascals. All right, so at this point, I actually have all the ingredients if we want to finish it out. have all of the ingredients to find my overall shear stress, my overall stress at C. So my overall stress at C would be the normal stress, 1.32 megapascals plus 63.2 megapascals. So my normal stress at C would be 64.5 megapascals. And then we know the shear stress at C is 0. No shear stress on the end there. All right, so we were actually able to finish out all of C, right? We applied superposition, just adding up this entire row together, right? Adding our normal stress that applies to both C and D. Add this C value for shear stress. He gets put in his own place. He's 0. And then the bending stress at C. So let's finish out our point D then. So at D, I'm going to have this guy, and then my moment is 0. So I actually don't need him. So what this means is that I actually already have my normal stress component for D, right? Normal stress at D is just 1.32 megapascals. There's no bending moment there. So it's only that normal stress that is constant through the whole face is there at D. The last piece I need is that shear stress at D. Right, this equation right here, let's go ahead and find him. We have I, right? We have our moment of inertia. We have V, the shear. Here's our shear. Here's our moment of inertia. We just need Q and T. Let's look at my cross section again. My cross section, my point D happens right halfway. My point D is right here. So this is where my Q area is going to be. So my Q area is going to be that 50 millimeters times 125 millimeters. 0.125. And that gives me a prime of 0.00625 from my calculator. And then I also need the centroid here. So the distance from my axis to the centroid is going to be half of 125, 62.5. The y bar prime is 0.0625. That gives me a Q value, multiplying those two together. 0.00625. Punch it into my calculator to get 3.906 times 10 to the negative fourth. Excellent. That's my Q value. My thickness, again, that's the width of what we're cutting through here. So my T value is going to be 50 millimeters, 0.05 meters. And those are finally all of the components that I need for this shear stress at D. So shear stress at D is the shear value, 21.93 kilonewtons, times the Q value we just found, 3.906 times 10 to the negative fourth, over moment of inertia, 6.51 times 10 to the negative fifth, times that T value. All right, so we got all those numbers. We go ahead and punch that in our calculator to get a shear stress value of 2.63 2.63 megapascals. And I guess that's the end of this example because this dog is in my face. 2.63 megapascals for shear stress at D. We'll be right back. All right, and we're back for one last example here with a solid rod with a radius of 0.75 inches. We want to determine the state of stress at point A. So if I kind of do a little cross-section zoom, enhance on our cross-section here, this point A is right at the outer edge of our rod here, but does go through the neutral axis here. So first things first, we're going to go ahead and cut through this rod and determine all of those reactions. So with this rod, you have two options with how you can cut it, right? You can cut it towards the wall, or you can cut it on this side with the 800-pound force at the very end of that rod there. And I would say do it on the side with the 800-pound force, because then you don't have to calculate all of the reactions at the wall. Instead, we can just go ahead and take this section. Here's the rod. Here is our cut through the rod. And I can look for all of those. Here's that 800 pounds. I can look for all of those reactions on this side of the cut. I don't need the reactions at the wall to solve for these. So here we have our forces. We have force Z, force X, and force in the Y direction, right? This is a 3D cut that we're making here. So we're going to have our 6 components, right? Our 3 forces and our 3 moments. Those moments, we have a moment about Z, MZ, a moment about Y, MY, and the moment about X, MX. 3 moments, 3 forces, 6 equations that we're going to be solving for. So I'm going to go ahead and just write out all these ones that I know, right? So easy enough to start with. Fx, there's no other component, no other force in the x direction, so Fx is actually just 0, right? There is no Fx. And same for Fy. Fy is also 0. The only force we have on here is the 800 pounds. So when we solve for Fz, we can see we have an 800 pounds going down. So Fz must be 800 pounds going up. Right? We can set up the whole equilibrium equation and solve it, or we can just see it's the only force there, right? There's an Fz in the positive z, there's 800 in the negative z direction, so the Fz has to be 800 pounds. And we can do it the same with the moments, right? So we can say, if I take a moment about the x-axis, I have that 800 pound force, right? So I take that 800 pound force, and I get a moment that is 800 times its distance away from the x. So this distance is 10 inches. So the moment about x is 8,000 pound inches, right? The 800 pounds times 10 inches. I can take my moment about y, right? And that's my distance from the y-axis to that z force again. This is 14. So the moment about y reaction that I'm getting, right, is just it's just counteracting this 800 pound force. So 800 times 14 gives me 11,200 pound inches. And then a moment about z, I can see I only have the one force. It's parallel to the z-axis, so there is no moment about z. So now, as I'm looking at all of these things that I have, I can look at all of the stresses that I actually have. So in this case, right? I have FZ acting as a shear stress, right? FZ is acting in this direction on our cross section. Let me do FZ is in green. The FZ is our shear stress, right? It's acting along the face of the cross section there. So this is going to be a shear stress of VQ over IT. Our MX, we look at MX here, it's going around in that same face of the cross section. So what that means is that it's creating a bending moment, right? If we look at the cross-sectional area, it's going in and then it's coming back out, right along that neutral axis at 0 there. So this is a bending moment. So MX is a bending moment. My over I. But very importantly, we notice, oh hey, A is actually on the neutral axis. So for a bending moment, we know that if it's on the neutral axis, the bending moment is actually 0. So it turns out there is no bending moment here. We don't actually need to use this MX's 8,000 value. So even though it's there, it's not doing anything at point A. If point A were somewhere else, say at the top of the circle instead, it'd be a different story. But since it is on the neutral axis, Y is 0, which means the stress is 0. There is no bending stress there. And then for this last one, My, you'll recall at the very beginning of this video, we talked about when we're looking at these sections, how to know where there's torsion. And you know when there's torsion, if your moment is going around your longitudinal axis. And so My is going around our longitudinal axis. So this is actually a torsion in this case, right? It's being twisted. You can imagine, it kind of looks like a little Allen key. Imagine twisting that Allen key. It's under torsion. You're applying 800 pounds of force onto that Allen key. So this My is actually a torsion. So torsion has a shear stress that is torque times radius over polar moment of inertia. So again, we just need to find these two shear stresses and there won't be any normal stress, right? We already ruled out that bending moment. So overall normal stress is 0. There is none. But now we'll find the overall shear stress. So we found our values. We have the 800 pounds for shear, and the 1,200 pounds is our torque. Okay, so the torque is 11,200 pound-inches, and our shear is 800 pounds. So now what we need to do is we need to go ahead and find all of our other cross-sectional properties so that we can go ahead and solve for these two shear stresses. So let's go ahead and we've got our little area there. We know that area. Let's take a look at the cross-section again. We need that Q value. So since A is here, Q is going to be this entire area above the centroid. Q is Y prime, A prime. A is going to be the area of the semicircle. And that Y prime, we're going to have to look up the centroid value of a semicircle. I think that would be the easiest way to do it. I'm sure it's in a chart for us somewhere. And let's see, when we do look that up, the centroid of a semicircle has the equation 4r over 3 pi. And then the area for a semicircle is 1/2 pi r squared. So we can go ahead and simplify this down. These pi's cancel and get one of these 2's to cancel with the 4. So I end up with 2/3 r cubed. So 2/3 times 0.75 cubed gives me 0.82125 inches cubed. All right, so I've got a Q value. It looks like the only other values that I'm going to need are the moments of inertia, the regular moment of inertia and a polar moment of inertia. So I, for our regular moment of inertia for a whole circle, since this is a rod, is pi over 4 r to the 4th, which is very similar to our polar moment of inertia, pi over 2 r to the 4th. So don't get those two confused. They are different. They have different use cases. They have different values here. So just know that they look very, very similar, but not to get them confused for a circle. The pi over 4, that's the regular moment of inertia, 0.2485 inches to the 4th. And then the J is the polar moment of inertia, which is twice that value. So now we have all of our ingredients. We can go ahead and plug into our equations here. So for torsion, our shear stress is going to be that 11,200 times the radius, 0.75, all over polar moment of inertia, 0.497. And that gives me a value of 16,901 psi. And then I'll plug in for my other shear stress equation. Let me do it a little farther down where I have a little more room. Tau equals, the shear was 800. Q we calculated 0.28125. Moment of inertia 0.2485. And the thickness T is this entire length here, right? This entire length at A, the thickness at A is actually the diameter. So don't do the radius on that. It is the full diameter, 1.5 inches. Punch that into a calculator and I get 604 psi. So the very last step, again, is your superposition, which is just saying, okay, I'm going to take these two shear stresses and add them together to get an overall shear stress. So the 16,901 plus the 604 gives me 17.5 KSI. All right, so the trick to these is just making sure you can find every individual component and then breaking down what you actually need, what is actually happening at the point of interest, because it's different at every single point. So knowing what point you're looking at is really critical for these problems.